So you already had one lecture, right? Right? Read your book. Okay, so this class would be mainly refresher on ODEs. If I would see that you're all following along, it's just boring. I will try to move ahead more quickly, but today is going to be mostly refresh. Okay, so first of all, my name is Naya Steinmetz. Okay, and I sit here in this building in room 218. And generally you can come visit whenever you want. I don't have office hours, but if I'm there, you are more than invited. And you are welcome to send me mails if anything is not clear. Okay, so we are going to talk about maybe differential equations. Okay, so it doesn't seem that this is a good one, so I'll try another. Okay, so let us start with something which is probably the obvious. So, a formal solution to any equation of the form y prime is equal to some x with, we are usually, okay, so we would call it a solution only if we have initial condition. So I would, if I'm not writing any initial condition, I'm assuming something of the form of x0 is x equal for some constants that I'm not worrying too much about. So the solution, the formal solution will be something of the form right? This would be the formal solution to, if we would know how to integrate this fx in this simple case, we would get a solution, right? Obvious. Okay, so I need to do an example for that. This is obvious, right? Okay. So moving ahead. The next best thing is separable case. So what is a separable case? It's when okay, so we have some is equal to some function. But we can separate it to two functions. One depends only on y, and the other which depend only on a. Right? Yes?
Y sub 0?
Well, of course. So about that, of course, if you see a mistake, tell me, mainly because they are filming it, so we won't want to cause any trouble to anyone watching. You can ask. Okay, so in this case, then we would have something like Let's see. Right, because we would just be able to integrate the two sides because every side depends only on one variable, so we don't have any problem to integrate. And okay, in general, we have a condition when an equation is separable, and it is followed from the following reason, because if we have some f of x and y, right, we know that the second derivative should be independent of the order of the differentiation, right? So we can just up there. So if I have something like is equals some, I don't know, f of y, right? Or I want it that, no, I want it that way. So okay, I can even do it more generally. I wanted to do it that way. Okay, so if I assume that there was any exact solution, then the derivative of f with respect to x is df dou f dou x plus dou f dou y dou x, right? Okay, I should have been more precise. I'm assuming that y is dependent on x, right? But I didn't made it explicit. Then I can, if this is equal 0, I can see this same pattern here, because this is this dou y to dou x, and this would be dou f to dou y. This will be dou y dou x, and so this should be dou f to dou. But if this is the case, then from this it follows that dou m to dou x should be equal to dou n to dou y. Okay? Maybe I use here a bad notation because then I need minus, right? Let me see what I did in my notes. Maybe, yes, there is. I used it that way, and then there isn't minus. Otherwise, one should put there a minus. Okay. So, a simple example. Any questions? Okay. So let's take the example of y prime is equal e to the x plus y. So is it obvious that it is separable? Right? It is fairly obvious. I don't need to check, so I would immediately So this is okay, so I can be more cautious about my integration, but I will just add a constant. What is it? Y, and here is it. And then I can claim that so if I take the logarithm, and what will be C, it is of course, I need it to be, right, let's plug in, for example, x equals 0 or x0, so and then if I'm taking the logarithm of that, I can see that y of x is minus of okay, clear, right? Okay, any questions? Questions? No. Okay. So next level is probably constant coefficients. So this is equation of the form the nth derivative plus of the y of the n minus 1 derivative until y. How will we solve that? Pretty easy, no? This is, you are all quiet because it is difficult, or because it's such obvious? I'm not sure. So we can plug in answers of the form e to the r x, right? And then this would become just an algebraic equations, because the exponents will be in all the terms. We just cancel it out. We would have r to the n, and here would be r to the n, and obviously there is some, okay, and here so if it is easier to as an algebraic equation, so this is as easy as a differential equation. If this algebraic equation is hard to solve, so this differential equation will be hard to solve. So, but there is one complication, and that is that we can have multiplicity, right? The degeneracy of the roots. What would happen if we have two roots, two that it is the same root, the same with twice. So we would have one solution, but we want to have n solution as the higher order of the equations goes up. We need another solutions to form the generalist or the complete solution of the problem. So, is this clear, or should I do an example of that? No, don't do an example? Okay, great, thank you. So, where did it? So, the other thing that we can do is, in general, we can write y of x is equal to, I won't write it formally, but as simple as that. If we have multiple, and then, okay, this, and it would still be a solution. If e to the rx is a solution, then every other power will also be a solution, so we should add more and more complicated terms. Okay. And another thing that can happen is that we can. Okay, so I won't go into it, but in the general case, you can have complex roots also. Okay, and then you just need to write the solution as sum of the two possible solutions, right? Because if complex conjugate, and you know that if you found one, then the other is also a solution. Any questions? Well, erase it. What we do first. Okay, so I would first explain the general case. So we have other class which called I guess, right? Right. And what is that? It is when we have some kind of differential equation, where here we have something which depend on y, not on x. Okay, so it makes it a bit more complicated. Okay, and it is get more complicated when we have higher derivatives, as always. But there are many cases where we can simplify autonomous equations and reduce them to non-autonomous equations, but of higher order. So, an example I would give. So there is something called equidimensional in X, which means that the equations is invariant under the scaling of X. Okay. If we just scale X up by some constant A, every solution will still be a solution. If we observe that our equation have this property, we can use it to simplify our solution. I would give example afterward, and of course there are also equidimensional in Y, where Y is go to AY, and we have something called scaling invariant, where X goes to AX and Y go to some A to the P Y. So to explain why is it interesting, think for example that if we adjust our measurement of length, then when we are dealing with the volume, okay, so there would be some power of the scaling. It won't be just one-to-one. So this is an actually interesting case. And there are many ways that we can simplify it. So for example, this one we can simplify by using X going to ET, I guess. This one, I guess it is Y going to X, P, U, E. This, I guess, is Y to 80. I will check it. I guess it's something like that. I would. Right. Okay, not exactly. But exactly that there is, of course, because this cannot be, because there won't be any X. So we should do something like that. Okay. So when we do that, we just plug it in the equation and we get another equation that would be most of the time simpler to solve. Okay? Because all those transformations, they conserve the scaling, they conserve the invariance that there is in the equation, and we can use them to simplify it. So I will do a simple example. Okay, so is it no, shit. Is it? This is okay. This is probably not a good example. It was an example for some. I meant to do this earlier. Anyway, this is an example of what this is. Because it is not clear, because it's not obvious that it will be any of the. But which transformation here would simplify these equations? This is not obvious because it's not going exactly as those ones. But if I already wrote it, let's solve it. Anyone have any yes? So you see that the powers of the x are growing with the derivatives, right? So if I would plug in here any power of x, I will reduce it to an equation with the same order, right? Because if I would assume something like that, right? So it would be pretty much this, but because I would have right? So this is more close to the constant coefficients case, but here it's not a constant coefficients, but we can, if we choose our transformation with some insight, we can reduce it also to an algebraic equation. What would be the solution of that? I wouldn't. Okay, so this is. Okay, we can see it that this is minus r, this is minus 8r, this is, so we can easily see that there is one root with multiplicity 2. So this is not enough, right? Because it is true that it is a solution, but it's not the solution, because we can also have something else. We have multiplicity. So the solution to such a case is to add I would add here a constant. Right? Because again, if I take this and plug it here, right? So if the derivative of the x to the r would still cancel from every one of them, as in this term, but the derivative of the y would cancel here because of those terms. I need to do it explicitly? Yes.
So if we have the JS and 2.
Yeah. So we had. So the question is, what if we would have higher? Okay, so we would need higher orders of the logarithm. Okay, this is our only way to generalize it. And in this case, this xr is 4, and then of course we need to use the initial condition to find those, to determine those constants. And since this is a second order equation, we obviously need two conditions in order to get two constants. Any other questions? Okay. Okay, another example, a bit more complicated. So I know that it may be too simple for most of you, but we are going to do many differential equations, so it is really for the best to practice it before moving on. Okay, so you can see that it is of a similar form than the previous, but it is not as simple. Why not? Okay, so what will be?
The roots will be imaginary?
Right. And the root would be imaginary. So we can, this is, so in order to solve that, we can say and here we would have 4. Right? Something like that. And of course this is imaginary. So we have just check myself. I did something wrong. What I did wrong? Root of 12.
No.
Here? Root of 12 over 2 and then, so this is root of 3. But still I had it multiplied by 2. Why? Why? Because well, It's -1, but why?
It's not -4, it's
Oh, right. I shouldn't ever try to do simple things on the board. I just look stupid. Okay. Okay, so what are we going to do with complex solutions? So I'll just tell you that the solution is in general something x to the power and I won't try to prove it here. Okay, so you can just plug it in and see that it does work, and I won't try to derive it. So in our case, it's just it would be C1 x -1. And then we add something like this. Okay. Questions? Okay, so our next kind of equation would be homogeneous and inhomogeneous first order equation. So first order So starting with the homogeneous case. So homogeneous case is just equal first order linear ordinary differential equation, I guess. I don't think we will touch upon nonlinear today. Yes, we won't. Okay, so how would you solve this? And of course, the non-homogeneous is just So let's start with how to solve this. Anyone? It is that boring that you don't, or is this? I really don't know, so I don't know if it is too easy or too. Okay, it's. Is it? You don't remember. Okay, so it's not too easy. Okay. That's all. Okay, so we did. So actually this is kind of separable equation, right? Because let's do it step by step. And let's us write it even implicitly as dy. Okay. So now it is clear that we can arrange the equation such that the y would be in the left hand, right? We can. And the solution of this is, of course, because we have here a log and here we have integration constants, we multiply, but we know that if this is 0, and we can even do it. But then we can set it from x0 to x, okay, and then the integral is vanished when it is x0, and y0 would be the value in x0 and not in 0. So it is pretty general. So the first case is pretty easy, unless G is something messy. But overall, it is solvable. This is also solvable, but a bit more difficult. So we would try to use our knowledge from the previous case to solve the second case. Okay, because we know what would happen if this would be 0, right? And we should always try to use the thing that we know. Okay, so I will do it in a bit different way, but I would try to so a way to see this solution can be to try to find an exact function that would behave in the following way, that this is something of an integration factor, right? So if I multiply y by some f and then take the derivative, it will be 0. Why is it close to that? Because if I would take it, it will be f y prime plus y f prime, right? So the thing that I'm looking here is just to write it like okay. So in a way, this is another way to see that the solution is exponential, because I'm looking for something that would be right? Okay, is it clear? Because I'm trying to find something that would reduce it to an easy equation, because this I can just integrate away. And this already tells me that I would need a function that would be f prime over f equal j, and this of course is log f is equal g. So I'm a bit troubled by the missing minus sign. There was some. Okay, we would find it. Okay, so now if I would try to solve this, I don't know why, but I started moving from right to left. Then I would get y is equal. Okay. Okay, this is the minus sign, because after I would some constant integration, right? Because I would integrate it, I would get here some constant, then I would have to divide by f, and f was just this exponent of g, because I wanted. Okay, so now with this kind of thinking, I can use it also in the other case. Because what did we find? We found that y times e in g dE is prime is equal to, right? Because the left hand side is exactly the same. Okay, agreed, right? The left side is exactly the same. So I'm using here the same trick that I did before. The only thing that is, of course, it was measurable choice to use the f, because now I do have f in the equation, but this was before another f completely. Okay, here we found it. It was, and now I would integrate it. I would find y. Why do I miss? Okay, so another thing. I cheated a bit because let's do it properly. Let's do it properly. We want y times some edge of x prime to be equal now f of x. Well, y but now I would need to divide by age, right? So this is what I missed before. So this is y. So now I have y. Just a moment about the signs. Yeah, I guess it will be like that. Why? Why? Because sorry. What did we say? We said it was okay. So h that this is the same thing. Then we get that. So here inside we have it is with plus, right? No. Okay, I'm missing a minus sign, but let us found it, because this is what I want, right? I want this to be that. So okay, this is the problem is that I want this. I want this to be that, so this should be equal to y prime. This should be equal to g y, and this, whatever that was, should be equal to f x, right? This is the point. Blah 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 blah. So this is times is equal to some, I don't know which letter I didn't use yet. I don't know. Z of it. Okay. So this is why to have this is to have y times g dx prime is equal to f e and so we found a solution of the form but we still need to take into account the initial condition or boundary conditions. And we know that the first equation is equal to 0. So we can always add the homogeneous solution, right? Any multiplication product of the first one. So the complete solution would be this is the general solution. And if here I write x0, I write here x0 to x, and here it would be y0. Right, because the integral I can always take from a point, and then here I know its behavior. Okay? I hope that it is understood. Questions? Okay, so example would be okay, so the first step would be to solve the homogeneous case. So the homogeneous case is just y prime is equal to is equal to so this is log y equal log x no. Okay. So we found, but I'm worried that I have a minus sign here when I didn't. Why? No, I added, I should have. Just when I rearranged the equation, I should have erased the minus sign. Okay. So in the terms of the explanation before, so this x squared is actually the exponent of log x, right? This is what of log x squared. So if I would look for the complete solution, it would be y equal y0 x squared plus, and here I have square is 2, and here it is over x dx. Not over x, because okay, I should have rearranged the equation explicitly, and then it would have been clear that, and I would and this is just my so this is minus 5 minus x 4 over and of course I shouldn't be so quickly to okay, so I did here something terribly wrong, because if y would be the solution in 0, it would be totally a mess, because I need to take into account the fact that this would diverge in 0. So let's just do it step by step. How did I do it before? I did it with, okay, with taking it x0 to x. So this is x4 over this is and now in x0, those terms would cancel out, and now I need another things here. Why? Okay, so all this is multiplied by x0 by x squared from here, but why? Okay. Okay, I did something wrong to the boundary conditions. I did something wrong with bad English. Boundary conditions, because I need to divide here by some, because here I should have something like, or something like that. I'm not, but where did it go? Why is it wrong? Need to check it. Okay, it was already here, right? Because here, if I try the homogeneous solution, so y0 is equal to a x, so a is equal x0 minus 2. So it wasn't y, it was 0. So okay. There is indeed here this factor, and everyone is happy. All is good, which and good. Questions? Okay. Comments? Something? Okay, so next item on the agenda is second. Oh, there. Yeah. So the general form is something like. Here, as before, we use the homogeneous solution to find a non-homogeneous solution, but here there is it is much more tricky because we have two solutions and we need to take some kind of a combination, and we also have the possibility that the solution are not, the equation is not well defined, and then we get a solution that depend on each other. So I would remind you of the Voskonian. Okay, so the Voskonian is the determinant of the kind of matrix of the solution and the derivative. And why is it good? Because we can write a particular solution. Okay, it won't necessarily be the only solution. As y2, y1 over x. No. Okay, so I probably should write here 1, 1, 2, and here is minus, I think. 1. And here I should add okay, so we first of all find two solutions for the homogeneous equation, and then we can find, using integration, which is usually a more straightforward problem, using integration we can find the particular solution for the non-homogeneous equation. So I just look for another one because Okay, so the problem with that is that even the homogeneous equation is not so easy to solve, and we should so we need here a bit of intuition to find it not but okay, so for the first of all I would transform it to our normalized convention, which will be x plus 1 over x y prime So one solution that one can maybe guess is e to the x. Because also always try something with e to the. So if we are plugging here e to the x, so this would be e to the x minus x plus 1 over x e to the x plus e to the x over x. So this plus this. So this will cancel this minus x over x is 1, so this would be 0. So if you, of course, don't know that it would be x to the e to the x exactly, you can always try e to the s of x. Okay? This is a guess that can give you intuition on what is going on. So if I didn't know that it would be e to the x, I would try something like e to the s of x. I try something like that. And then I would say y prime is and y double prime is and this is something that you would, I guess, be pretty comfortable after a course. Not like so, and then I would have got something like and maybe here someone would have, now you would call S tag F or Y or something, and then you would have a simpler equation. So I'm emphasizing this because it is much easier to read from the books the solution and then to show that it does work. But if you don't have, so this is the ugly way that you can go solving, for example, when you have your homework and you don't have the solutions and you try to find it. So this is kind of a way that you can try, okay? So exponentials are something worth checking. And here we have another solution that we need to find. And actually, one can see that x plus 1, if you take the second derivative of that, is 0. If you take the first derivative, it's just 1. So it will be x plus 1 minus x plus 1, and it is 0. So this is the other solution. And then one should take the Wasconian and take the integral and get some ugly expression that I would not waste your time on that. Instead, any question before I move ahead? Something? No? Okay. So, I want to talk a bit about singularities. Because, for example, when we dealt with the non-homogeneous equation, I just divided by gx as if it is clear that it won't get me into trouble, but I may very well just get a divergence, right? If my gx has some 0 somewhere, I just divide it by 0 and open the gates of hell. So one shouldn't do that. At least not if we want to solve at the end. So if we have a general solution, so we have those derivatives, right? Plus a and here we have 1 okay, so we have some okay, so here it would even depend on x. Just any equation. If here I am looking at equation that where the higher order is with constant 1 before, so it's normalized that way, and then we can investigate the singularities looking at the coefficients of the other orders. Okay? So if an equation doesn't have any zeros there, any singular divergence in the coefficients, then the point is called ordinary point. Okay? Or we sometimes call it OP, ordinary point. It is just a point which nothing very terrible happens. So in that point, the function is said to be analytic, right? So we can expand it in Taylor series and do any number of nice things. But we get into trouble when those coefficients does diverge. Okay, they can diverge in many ways. Okay, so they can diverge, for example, like 1 over x. They can diverge like 1 over x squared. Right? They can diverge in many ways, and it depends on which derivative coefficients is diverging and in which power. Okay, so as we go to higher derivatives, we can kind of support worse divergence. But as we are on the other, so so I will define it like rigorously as x minus f to the power n times a. And now I should be careful about my indexes. Okay. Now the question is what is the behavior of some power times these coefficients? Okay? Because if it would be just 1 over x 0, right? And this is 1. No, let's talk about something concrete. So we have y double prime times p of x y prime plus q of x y equals 0. So n is equal to, right? So let's assume we are talking about the first derivative. So this would be assume that p of x goes like 1 over. Then you can see that it won't diverge, right? So this case of like weak diversion is called regular singular point. Singular point. If it is worse than that, we call it irregular. Okay? So example would be y prime y over 2 So this is just ordinary point, right? There isn't anything bad happening in any point of this equation, and it is not surprising because the solution of this equation is just y is equal, and we know that the exponent is analytic everywhere, so not surprising at all. Here we see regular singular point. Okay, and here we see irregular singular point because the power of the divergence is higher than the place in the lower the derivative. But there is another point here, which is that we may ask what happens at infinity. Okay, so does any of them diverge at infinity? Is the infinity a ordinary point, a regular point, or irregular point? And it may very well be interesting question if we want to expand this solution near infinity. We want the steady state or something like in the infinity. So what we are doing when we try to answer the question of infinity? So the method to address the infinity is just to transform it using the transformation is x going to 1 over t. Because anything that happened to x in infinity would happen to t in 0. Okay? So it is Straightforward. So, so I would want to write it y as the equation of t, right? When I t of x. So t equals 1 over x. And 1 is equal to 1 d and d and now we see that this is so what we have to get here here we have and now we want to ask what is the behavior of t equals 0. And we see that it just flipped, right? Because now I would just cancel this with that, and I get here ordinary point. There is nothing bad happening at infinity for the question. This would stay singular point. Here we would get singular point. Well, of course, we divide by the coefficients of the higher derivative to bring it to the same form as before. Okay? Is it clear? So in your homework, you would have the chance to play with this and to classify points. And why is that important? Because we want to know how is the divergence look, to know how to approximate the function. For example, if we have ordinary point, it's straightforward to do, even if I don't know to solve. Let's say I don't know how to solve y tag is equal y. I don't know, maybe over x, okay, y, okay. So since there isn't any divergent here, I can try and just Taylor expand it. Right, I can, right. Prime is equal. And then solve one by one. I would get sum n a n. What I'm seeing, I can see from here, I can see that n plus 1 is equal. So a n is equal 1 over n. And voila, we found the Taylor series of the exponent. Okay, so here it was easy because I didn't want to try and do something that I didn't prepare for some ugly function. But it would work also for difficult functions, okay? The problem would be many times to go from the recurrence relation to express it as something in closed form. It's not always that obvious, like finding factor. And you would get comfortable with gamma function and it would be better. But if we are dealing with singular point, so we can't use Taylor series. There is divergence, so we can't expect that there would be Taylor series there. But we can use a very close method called Feminist Method. Okay, so I don't have time. But Feminist Method is actually to write something like x to some alpha and do exactly the same. Okay, we will talk about it, I guess, next week. I would upload and problem sheet as soon as I would okay it with Jonathan. And if you have any questions, feel free to ask. And problems with the exercise, problems with the problem sheet, just ask away, please. So I would get a feel what's going on.